Okay, time for the logic gates. Logic gates, yes. What are gates? Gates are basically, if a gate is open, you can go in. If a gate is closed, you may not come in or go out. All right, by the way, if a gate is open, you may come in or go out. And then when the gate is closed, that is what? You may not come in or go out. Now, unfortunately, with the electrical gates, the logic gates, it's other way around. When a gate is closed, actually it means you can go through, power can go through. When a gate is open, actually power can also. It's a little bit twisted. Now, with the logic gates, basically we're going to look at I'll start off with the what? I'll start off with the basic gate, the NOT gate. Let me do that. Let me start off with the NOT gate. The other gates, I'll come back to them later. Okay, the NOT gate, what is it? What I like about this gate is that if you listen to the name tells you what's supposed to happen. With the NOT gate, this gate is not supposed to be closed if you're going to get what? An output. All right. Remember, the desirable thing is the output. So if a gate is named according to what? According to when does it actually give us an output. So with the NOT gate, I will give you the basic circuit of that. The basic circuit is something like this. I'm sure you will say, I've seen this somewhere. I've seen this circuit somewhere. What circuit is this? If you look, we've got a power supply, we've got a transistor there, we've got an open input. This is an open, the base, the input. It's an open input. There's no base. Yes, we've seen this somewhere. It is, of course, where we say the transistor operating as a switch. What happens? If I have an input coming in there, when the input is below a certain level, the transistor stays off. When the input is at the what? It goes below. If the input is at a certain minimum or above, the gate will what? The transistor will conduct, and then when there's what? When the power the input A drops below a certain level, and then the transistor will go off. So this is basically transistor working as a switch. Yes, we've seen this before. Hopefully, it's just an open input transistor circuit. Now let's see how this actually works. I'm saying this is basically our NOT gate. Our NOT gate is simply supposed to be when you say the output here, our output is not A. Remember, this is binary systems, and it's either we've got something on or off. Now I'll come back. Let me come and explain what I will call the what. We've got two scenarios here. We have what is called positive logic. With positive logic, okay, with positive logic, a 0-volt signal is represented as a 0, which actually means off. Okay, and 5 volts is represented by a 1, and that actually means on. Okay, this is when we are dealing with positive logic. Okay, now we have also what is called the negative logic. Now it's the other way around. With negative logic, 0 volts actually means 1, which is on. It's the other way around, like I said. And 5 volts is actually what? A 0, represented by a 0, and this actually means off. All right. So most of the circuits we are going to be dealing with what? With positive logic. All right. With positive logic, now we have to remember that we said the number of inputs determines the possible combinations. So this gate here can only be one on or off. This input here can only be on or off. Let's look at what we call the truth table. The truth table. Truth table is a table that considers all possibilities, all possible combinations, and tells us what the output will be in those scenarios. So we call this a truth table. It must not eliminate, it must not have any condition missing. Otherwise, then it's not telling the whole truth. If you don't tell the whole truth, then obviously it's not truthful. But if you say if you go home to your family, to your wife, and you say to your wife, you know what? I went to work, and from work I drove home. I passed by ShopRite, I picked up a few goodies, and here I am home. And you forget to mention that you passed there and you saw a certain makumalo, madlodlo, whatever. Ne? You're not, you told the truth, but you told part of the truth, and therefore that does not qualify. You still say it's a lie. So that our truth table, therefore, we have to include all possibilities. In this case, we have an input A. It can only be off or on. Remember, the truth table also has the number of conditions is 2 to the power of n, where n is the number of inputs. We have only one input, 2 to the power of 1, 2 conditions, on or off. And the output, we will have to then see how the circuit would respond. So remember, 0, we're using positive logic. 0 means 0 volts. So if we have 0 volts here, what does it mean? It means that this is either left open or it has been physically grounded. No, it has been physically grounded. All right, either it's left open or it's been grounded. So remember, it doesn't matter which one you choose. So let's suppose ultimately we've got 0 volts in there because there's no power being supplied. Now, if there's no power being supplied, there is no basis for us to think that this guy should be biased. Where is the biasing? It's got 0 at the base, so there's no sufficient voltage. We need a minimum of the threshold voltage, 0.3 in the case of germanium, 0.67 or 0.6 or 0.7 in the case of silicon. We need that minimum to actually drive this guy on. So now we have 0 volts, therefore this is off. If this is off, remember our transistor can either be in the state we are talking about now, which is what? Which is not, it doesn't have sufficient biasing, therefore it will be in an off condition. Now, if this is off, if we are wiring through a broken circuit, if the transistor acts like a broken circuit, there is no current that's going to flow through the what? Through, let's call that RC. This is the collector side. So let's say there's no current that's going to flow through the circuit. RC is therefore going to have what? Through RC there's going to be no current, therefore RC, the voltage drop there is going to be 0. If the voltage drop here is 0, there's no drop from the VCC, our output is going to be what? Our output is going to be 5 volts. Let me rather say 1. Why? Let me rather say 1 because I'm using the symbolism. 0 symbolizes a what? A 0 volts, and 1 symbolizes a 5 volts. So let's just say our output here is going to be 1. It is the opposite. It is not, we have got 0 or 1. So if it is not 0, it is going to be a 1. So our output is a 1. Now on the other hand, what could happen is that we could then decide, no, we want to supply A with a voltage, we take it high to 1. So we take our power from the source and we bring it there, and we say, now what if A is wired to the supply? This therefore will have a closed path from supply all the way through, let's call that R base. It is the base resistor, through the base, through the emitter, this is the PE junction, and to ground. So it's a complete path. So our transistor will develop its threshold voltage. The current will depend on the value of RB. Okay, we want to have an RB that is going to be sufficient, so that our other possibility with the transistor is what? It's going to be saturation. When the transistor is saturated, it basically behaves like a closed switch. So the two possibilities for transistor, for this transistor, is actually what? Open circuit when there's no sufficient biasing, or saturation where it behaves like a closed wire. If we close this, if this was a closed path, if this was a closed path, if it was like a wire, then you can see that ground is now connected direct to the output. Ground is 0 potential. We can't have it now being a what? Being a 1, because it's not the potential of ground. It is therefore going to be a 0. So our input was the voltage, which is, we assume 5 volts. We assume our VCC was equal to 5 volts. But that 5 volts, what it did was turn the transistor into a wire, and then that wire pulled ground to the output, and therefore our 5, remember I said I'm actually contradicting myself here, so I'm gonna use symbols rather than the actual voltages. So our 1 here has been changed to a 0. Not 1 is obviously 0. There's only two possibilities, 0 and 1. So if it's not 1, it's going to be what? A 0. So you can see now that the NOT gate will have changed that what? That 1 to a 0. So we either have, we've got two extremes. We have our transistor either conducting and being a short, or not conducting and being an open, and our gate is going to respond accordingly. So now we can see that our what? I'm removing the values. I just want the general circuit to remain without any values. We can see that if the input is a 1, it is converted to a 0, it's inverted to a 0. So the other name for the what? For the NOT gate is actually called the inverter. Not the inverter we use to what? For our AC supply from DC, or not the inverter that we use with our solar systems, but just the NOT gate. Okay, in this case, all it does is invert a 0 into a 1, or a 1 into a 0. So what do we see? We have, basically, we should know our name, symbol, the symbol for this gate. We can't always be drawing this. Sometimes in books we can't always be drawing these circuits, so we have symbols for them, but we know they mean our circuits. Remember the two extremes is either open or closed, depending on the what, on the biasing at the base, the input A. So our gate, this is the circuit. We have the truth table, which must tell the whole truth and nothing but the whole truth. Okay, and then we have got the symbol. The symbol, sometimes it's not practical to always be drawing our actual circuits, and sometimes the circuit is actually a little bit more complex than this. This is just a basic circuit. So the symbol is simply a what? An input into a buffer. This is a buffer, but we invert with a little 0 in front, so that our input A is inverted and our output is the opposite, bar. Bar A means the opposite of what? Of A, the inverse of A. All right, so this is our symbol. This part of the symbol, this part here, is called the what? It's called the Boolean, from the guy, from Mr. Boole, who helped us with this, with a Boolean equation. Okay, so we'll ask in tests and exams, we'll actually sometimes ask for the Boolean equation. We'll ask for the symbol, which must have the input and output, and then we'll ask for the what? We may ask you for the circuit, for the basic circuits, and the truth tables. All right, there is something else though. It's also not practical sometimes in explanations to keep drawing this. Sometimes we make it simpler with what we call the switch equivalent circuits. With switch equivalent circuits, where we use a combination of switches, just to explain how our gates work. We call them switch equivalent. Okay, equivalent circuit. CCT means circuit. So our switch equivalent circuit is simply, in this case, it's our supply with, it would be okay to just put a switch and then in parallel we call the switch our input, and then we say there is our output, and we call our output any symbol we like, Z a lot. Right, but then now this, however, is a dangerous circuit to draw, because in practice now it shows that people don't understand their basics. We've had a session where we looked at a scenario where what happens if we close the switch here, we eliminate this. When you eliminate Z there, now there is no resistance in the circuit. When you've got no resistance in the circuit, what happens here? Let's see. V. Alright, let's try and see what happens with the current if there's no resistance in the circuit. Remember, according to Ohm, I is equal to V over R. Now we are saying we have a resistance. We don't care what the value is. In this case, V supply. We don't care what the value is. Alright, I will say does not matter, but we are dividing by 0. When you divide by 0, because we are saying if we close here, this is eliminated and the resistance is 0. Alright, so that will be an explosion. This is where we see arcing coming from. This is where we see sparks, those violent sparks. It's an undesirable situation. So what do? We show It is therefore inexcusable to forget the resistor. In the event of closing the circuit there, we will have disaster if we do not have what? If we do not have a resistor to protect our source. So obviously it must of what is the what? Typical test question. This here must be of sufficient resistance. All right, sufficient resistance to what? The quality of the what is the resistance quality of the series resistor? It must have sufficient resistance to avoid what? To avoid overcurrent, too much current that will destroy our system, our supply, and while it is not big enough to what? To actually affect our circuit in the event where we have zero here. Remember, when we open here, we have zero. So this power is forced therefore to what? To go through Z, and therefore Z will be on. So when you have 0, Z will be on 1. Now, so the resistance here should not be too high to what? To sponge all the circuit out of Z, so that it does not what? It's not able to go on. So 1, the RS must be when we, after we've done this, so this is no longer true. So we remove this. So remember that RS must be of a value that does not suffocate, must not suffocate the load. Okay, it must not be too high to suffocate the load. Okay? Oh, Lord, have mercy. The load. Okay? While it must be high enough, to protect our what? The supply. Okay, so it must not be too high to kill the load, but it must be what? This is a knot. Okay, RS must not ow, where my dot, must not suffocate the load while high enough to what? While remaining high enough to protect the what? The supply. So I hope this so what do we know? We need to know that our what gate are we dealing with? Know its circuit, know the symbol, the Boolean equation, in this case Z is equal to not A, and then the switch equivalent circuit, and don't forget the truth table. All right. Also, please remember RS may not suffocate the load, but must be high enough to what? To protect our load. All right. With that, I believe that we should understand our NOT gate a little bit better. All right then. Ciao. I had fun. I hope you did as well.